The 1877 and 1878 El Niño killed approximately 50 million people. It remains the strongest event in any climate record going back roughly 150 years. The U.S. National Oceanic and Atmospheric Administration has now confirmed a 61% probability that a comparable Super El Niño will begin between May and July of 2026, with peak intensity rivaling that historic event. The standard impacts, coastal flooding, drought across the tropics, a new global temperature record, are being widely forecast. The most consequential effect of this event is not. By the end of this video, you will know what it is and why the timing could not be worse. Let's get into it. The U.S. National Oceanic and Atmospheric Administration's Climate Prediction Center has placed the probability of El Niño onset during the May through July 2026 window at 61%. That is the official number published in the most recent 4-season outlook, and it is the highest pre-onset probability NOAA has issued for a developing Super El Niño since the run-up to the 2015 to 2016 event. The classification matters as much as the probability. NOAA's April 18, 2026 4-season outlook described the developing event with 2 specific words: potentially very strong. That language is not casual. It is reserved inside the agency's forecast vocabulary for events expected to land inside the small reference class of confirmed Super El Niños observed in the satellite era. The language has only been applied a handful of times in the modern record, and every previous instance corresponded to an event that ended up reshaping global weather patterns for the year that followed. The numbers behind the language are striking. The consolidated multi-model forecast points to a peak Niño 3.4 sea surface temperature anomaly somewhere between plus 2.0 and plus 2.75 degrees Celsius by the boreal autumn of 2026. The most aggressive ensemble members are projecting an event that rivals or exceeds the legendary El Niño of 1877 and 1878. That event killed roughly 50 million people through famine across India, China, Brazil, Java, Morocco, and Ethiopia, and it stands as the strongest El Niño in any reconstructed climate record going back roughly 150 years. That is the comparison the 2026 forecast is now drawing. Not the 2015 event, not the 1997 event, the 1877 event, and the developing trajectory is closing fast on the threshold required to confirm it. The current Oceanic Niño Index, the standard measure NOAA uses to declare and rank ENSO events, sits at minus 0.16 degrees Celsius for the January, February, and March 2026 season. That reading is officially neutral. It is not yet El Niño, but the trajectory is what matters. 5 months earlier, in October, November, and December of 2025, the same index was reading minus 0.55 degrees Celsius. That is firmly inside La Niña territory. The shift from minus 0.55 to minus 0.16 over 5 months represents a roughly 0.4 of a degree warming, which makes this one of the fastest cool-to-warm ENSO transitions on record. The Pacific is not drifting toward El Niño. It is racing. The trajectory closely mirrors the 2014 and 2015 ramp that preceded the catastrophic 2015 and 2016 super event. In that case, the basin transitioned from neutral conditions through spring and early summer of 2015 and locked into Super El Niño territory by autumn. The 2026 ramp is on the same shape and the same timing. The probability data confirms the trajectory. The International Research Institute for Climate and Society publishes a probability plume each month showing the model ensemble likelihood of each ENSO category: La Niña, neutral, weak El Niño, moderate El Niño, strong El Niño, across each upcoming 3-month season. The April 2026 plume has the El Niño category climbing through the year, 70% for April, May, June, rising through summer, reaching 88 to 94% by the September, October, November, and October, November, December seasons. By autumn, the probability of an El Niño being underway is essentially certain. The CFSV2 ensemble, NOAA's flagship coupled model, peaks near plus 2.1 degrees Celsius, Niño 3.4 anomaly by October, November, December 2026. The North American multi-model ensemble mean shows plus 2.0 to plus 3.0 degrees Celsius across the central and eastern equatorial Pacific for the same window. The Central September 2026 estimate sits near plus 2.2 degrees Celsius absolute, with several individual ensemble members reaching as high as plus 2.75 degrees Celsius. What makes the ramp speed concerning is what it implies about the eventual peak. Rapid cool to warm transitions tend to produce stronger peaks because the subsurface ocean heat content has been building during the La Niña phase. and that heat surfaces faster when the atmospheric circulation shifts. The 2026 setup has both the speed and the heat, and the models are converging. The phrase Super El Niño is not marketing. It is a defined classification. The threshold is conventionally taken as a sustained Niño 3.4 anomaly of plus 2.0 degrees Celsius or higher. Events that meet this threshold are categorically different from ordinary strong El Niños in their global impact, and the historical sample is small enough that the entire reference class can be named. In the satellite era, meaning since reliable global ocean temperature monitoring began, there have been 3 confirmed Super El Niño events: 1982 and 1983, 1997 and 1998, 2015 and 2016. 3 events in 43 years. Each one rewrote the global weather pattern for at least 18 months. Each one drove a measurable jump in global average surface temperature. And each one produced humanitarian and economic damage that rippled through the years that followed. Beyond the satellite era, the strongest pre-instrumental candidate is the 1877 and 1878 event. The reconstruction comes from coral oxygen isotope records, shiplog sea surface temperature observations, and historical documentary evidence. The 1877 event was associated with the global famine of 1876 through 1878, which killed an estimated 50 million people across India, China, Brazil, Java, Morocco, Ethiopia, and several other regions. Through coupled drought, monsoon failure, and crop loss, the mortality was magnified by colonial-era food system policies that prevented relief grain from reaching famine zones, and the academic literature treats the event as the most severe single climate and food system disaster in recorded human history. That is the reference class the 2026 forecast is now being compared to. NOAA is not invoking the comparison casually. The numbers force it. A peak Niño 3.4 anomaly of plus 2.75 degrees Celsius at the upper end of the current ensemble forecast would place 2026 inside or above the upper bound of the 1877 reconstruction. The frequency of these events is also accelerating. Kai et al. Published in 2014 in Nature Climate Change projected that extreme El Niño frequency would double under continued greenhouse warming, moving from once per 20 years to once per 10 years. If 2026 verifies as a super event, that will make 4 super events in 47 years of the satellite record, a frequency that already exceeds even Kai's projection. The system is becoming more volatile faster than the models have been able to keep up with. But the comparison to 1877 needs an honest caveat, and it leads directly into the next point. Climate scientists have introduced a new metric in 2026 that puts the standard comparison in context. It is called the Relative Oceanic Niño Index, or RONI for short, and it changes the headline reading. The traditional Oceanic Niño Index measures the absolute temperature anomaly in the Niño 3.4 region against a fixed historical baseline. The Relative Oceanic Niño Index subtracts the long-term tropical Pacific baseline warming from that anomaly to produce a relative reading that compares fairly across decades. The reason this matters is straightforward. The entire tropical Pacific is roughly 1 degree Celsius warmer in absolute terms than it was in 1877. So an absolute Niño 3.4 anomaly of plus 2.5 degrees Celsius in 2026 is being measured against a baseline that is already warmer than the baseline 1877 was measured against. The absolute number rivals 1877. The relative number, properly baselined, does not. Both indices are now being reported in parallel by the climate community, and the distinction matters for honest comparison with the past. The 2026 event will likely be a top-tier super event by absolute measure. By relative measure, it will likely fall somewhere inside the top 5 satellite-era events, but will not necessarily be the strongest in the comparable reference class. This is not a downgrade of the warning. The atmospheric and oceanic impacts of a plus 2.5 degree absolute anomaly will land on a planet that is already warmer than the planet that handled the previous super events. The absolute heat in the system is what drives the impacts, but the comparison to 1877 needs the relative baseline footnote attached, and any honest discussion of the 2026 forecast has to include both indices side by side. The reason this is in this video is to prevent overreach. The carbon cycle implication discussed later in this video is real and is grounded in peer-reviewed attribution science. The 1877 mortality comparison is more complicated and depends on assumptions about what modern food systems can absorb that did not exist in 1877. The honest framing keeps the strongest claim on the strongest evidence, and that evidence is the carbon cycle, not the famine reference class. The standard primary impacts of a super El Niño are well documented and globally distributed. Most of the major effects are forecast with high confidence months in advance, because the same patterns have repeated across the satellite-era reference class. Coastal Peru and Ecuador get hit first. The displaced warm water that defines an El Niño collects against the western coast of South America, suppressing the cold Humboldt Current upwelling that normally feeds the regional fishery, and triggering anomalous heavy rainfall over normally arid coastal terrain. The 1997 and 2015 events both produced catastrophic flooding through coastal Peru, with infrastructure damage in the multiple billions of dollars and significant loss of life. The 2026 event is forecast to repeat the pattern beginning in late 2026 and intensifying through the first quarter of 2027. The southern United States typically sees a wet, cool winter under super El Niño conditions, with the subtropical jet stream displaced southward and atmospheric river events lining up across California and the desert Southwest. The northern United States typically sees a milder winter than normal, with the polar jet displaced northward. The Pacific Northwest tends to be drier than normal. These patterns are robust across the reference class, and the 2026 event is expected to reproduce them. The drought impacts are equally well forecast. Indonesia, eastern Australia, the Philippines, parts of southern Africa, and the Amazon basin all enter elevated drought risk during super El Niño years. The Indian monsoon weakens in the worst-case scenarios, with documented monsoon failures during the strongest historical events. The 1877 event collapsed the Indian monsoon for 2 consecutive years, which is the proximate driver of the famine mortality from that period. The 2015 event produced a weakened but not collapsed Indian monsoon, with measurable agricultural impacts but no famine-scale mortality. The temperature impacts are global. The warm tropical Pacific exhales heat into the atmosphere during El Niño years, and that heat distributes globally through atmospheric circulation. The consolidated forecast already places 2026 on track to become the second warmest year on record, even before the full El Niño signal develops. The number one position will likely shift to 2027, which will absorb the full El Niño signal as it transmits through the atmosphere. The 2 warmest years in the modern instrumental record are likely to be 2024 and 2027, with 2026 sitting between them as the bridge year. For the Atlantic hurricane basin, El Niño typically suppresses development through enhanced upper-level wind shear over the Caribbean and tropical Atlantic. The 2026 setup is complicated by the fact that the Atlantic Basin SST baseline is at or near record warmth. The shear suppression from El Niño may not fully offset the energy available from the warm basin, and the timing of the El Niño onset relative to the August through October hurricane peak will determine whether 2026 finishes above or below the elevated basin baseline. The forecast is uncertain on that specific question. For the Pacific Basin, El Niño elevates tropical cyclone activity. The 2026 setup is favorable for an active Western Pacific typhoon season and elevated Eastern Pacific activity. Coastal Pacific Mexico, Central America, and the Hawaiian Islands all enter elevated tropical cyclone risk through the second half of 2026. These are the standard impacts. They are being widely forecast and widely covered. They are not the reason this video matters. Before getting to what the carbon cycle implication actually is, the magnitude forecast needs an honest caveat. ENSO forecasting has a documented weakness called the spring predictability barrier, and the 2026 forecast is currently sitting inside it. The spring predictability barrier is the observation that ENSO model skill drops sharply when the forecast is initialized in March, April, or May. The reason has to do with the seasonal cycle of tropical Pacific atmospheric and oceanic dynamics. The spring months are when the system transitions between annual phases and is most sensitive to small initial perturbations. Models that perform well in late summer and autumn forecasts often diverge significantly when run from spring initial conditions. The CFSV2 model in particular is known to overshoot El Niño peaks in some ensemble configurations, especially in years with large warm subsurface heat content reservoirs. The North American multi-model ensemble shows confidence at 6 to 8 month lead of roughly 40 to 50% skill, meaning even with multiple models combined, the forecast is essentially a coin flip plus signal at that range. The 61% probability NOAA is publishing for the May through July 2026 onset reflects this barrier. It is not a 90% certainty. It is a probabilistic forecast made under acknowledged forecasting limitations. A strong but not super event with peak between plus 1.6 and plus 1.9 degrees Celsius is also inside the forecast envelope. The carbon cycle implications described later in this video apply most strongly if the central super event scenario verifies. They apply less strongly to a strong but not super outcome. The verdict on the magnitude question will arrive when the spring predictability barrier breaks in May and June. The monthly ENSO updates from NOAA, the IRI, ECMWF, the UK Met Office, and the Australian Bureau of Meteorology will sharpen through summer. By July or August, the magnitude question will be effectively resolved. The current forecast is the best available signal, but the next 90 days will compress the uncertainty significantly. This is the framework to hold while the rest of this video discusses the carbon cycle implication. The implication is real. The magnitude is uncertain. Both are true. Here is what the news cycle has missed. The standard primary impacts of the 2026 Super El Niño. The Peru floods, the southern U.S. flooding, the Indonesian and Australian and Amazonian drought, the second warmest year on record temperature signal, are being forecast and reported widely. The mainstream coverage of the developing event has been nearly exclusively focused on this category of impact. Almost no one in the public conversation is talking about what a Super El Niño does to the world's tropical rainforests, and that is the most consequential effect this event will have. The basic carbon math sets the stakes. In a normal year, the global terrestrial biosphere absorbs approximately 3 to 3.5 gigatons of carbon, roughly 11 to 13 gigatons of carbon dioxide, more than it emits. The global ocean absorbs roughly another 2.5 to 3 gigatons of carbon. Together, these two natural carbon sinks remove approximately half of all human carbon dioxide emissions from the atmosphere every year. The other half stays in the air and drives the long-term increase in atmospheric carbon dioxide concentration measured at Mauna Loa and the Global Monitoring Network. Of the terrestrial sink, the tropical land biosphere, the rainforests of the Amazon, the Congo Basin, and Southeast Asia historically contributes the largest single component. In a neutral or La Niña year, those forests are net carbon sinks. In a strong El Niño year, they have repeatedly flipped to being net carbon sources. It happened in 1997 and 1998. It happened harder in 2015 and 2016. The 2026 Super El Niño is the next major test of whether that pattern holds and whether the forests can still recover after the event passes. This is the implication the news cycle has missed. It is grounded in peer-reviewed satellite attribution science, and it is the reason the 2026 forecast matters beyond the standard impact list. The historical record is specific. The 1997 and 1998 Super El Niño produced an atmospheric carbon dioxide growth rate spike at Mauna Loa from approximately 1.5 parts per million per year in 1996 to approximately 2.9 parts per million per year in 1998. That was, at the time, the largest annual jump in the continuous instrumental record and roughly a 100% increase over the prior baseline. The mechanism was identified in subsequent attribution work. Page and colleagues, publishing in 2002 in the journal Nature, documented that the Indonesian peat fires of late 1997 alone released between 0.81 and 2.57 gigatons of carbon to the atmosphere. That was equivalent to 13 to 40% of the entire annual global fossil fuel emission total at the time, from a single fire season in a single region. The fires burned in tropical peat forests on Sumatra and Borneo, where centuries-old waterlogged peat domes that had been accumulating carbon since the last glacial period dried out enough during the El Niño-induced drought to ignite. Once the peat ignited, the fires burned underground for months, immune to surface rainfall, releasing carbon that had been sequestered for thousands of years. The visible expression at the time was the Southeast Asian haze crisis of 1997, which closed schools and airports across Indonesia, Malaysia, and Singapore, and caused tens of thousands of premature respiratory deaths. The satellite imagery of the haze became the defining documentary record of the event. Beneath the haze, the planet was running an experiment in fast tropical forest decarbonization at gigaton scale. The 2015 and 2016 Super El Niño produced an even larger and better attributed carbon pulse. Atmospheric carbon dioxide growth rate at Mauna Loa rose from approximately 1.9 parts per million per year in 2014 to approximately 3.0 parts per million per year in 2016. That was a new record. Total atmospheric carbon increased by approximately 6.3 gigatons of carbon in 2015 and 2016, of which the human fossil fuel contribution was roughly the same as in surrounding years, meaning approximately 2.5 gigatons of carbon of the increase came from somewhere other than power plants and cars. Liu and a large international team publishing in 2017 in the journal Science used data from NASA's then-new Orbiting Carbon Observatory 2 satellite to attribute that 2.5 gigaton anomaly geographically. The paper found that the tropical land regions, taken as a whole, released approximately 2.5 gigatons of carbon more than they would have in a neutral year. Critically, the paper showed that the three major tropical rainforest regions each released that excess carbon through a completely different mechanism. The Amazon basin released its excess primarily through reduced photosynthesis. The 2015 and 2016 drought was the worst on record for parts of the Amazon, and trees responded by closing their stomata, dropping leaves, and reducing carbon uptake. The Amazon was not burning unusually intensely. It was simply not absorbing carbon at its normal rate, and the missing absorption shows up as a positive flux to the atmosphere. Africa's tropical forests released their excess primarily through elevated ecosystem respiration, driven by anomalously high air temperatures. Warmer nights and hotter days speed up the biochemical breakdown of soil, organic matter, and dead plant material, and that respiration releases carbon dioxide directly. The African signal was almost entirely thermal. Tropical Asia, primarily Indonesia, with peat fire activity centered on Sumatra, Borneo, and Papua, released its excess primarily through fire. The 2015 Indonesian fire season was one of the worst on record, with daily emissions during peak burning exceeding the daily fossil fuel emissions of the entire United States. The fire emissions estimate from Field and colleagues in 2016, published in PNAS, was approximately 0.89 gigatons of carbon dioxide. What the Liu attribution paper demonstrated is that the global terrestrial biosphere did not just lose its sink capacity during the 2015 and 16 event. It actively reversed direction. The forests stopped buying time and started spending it. 3 regions, 3 completely different mechanisms, 1 net result. And 2026 will be the 3rd major test of this same system, but on a baseline that has changed. Here is what has changed since 2016. 2 pieces of subsequent peer-reviewed evidence have reframed the question from being a strong El Niño year anomaly toward being a possible chronic shift in baseline. Hubao and a large international team published in 2020 in Nature the result of a long-term forest plot inventory across both the African and Amazonian tropical rainforests. The conclusion was that the carbon sink in intact African tropical forests has remained stable since the 1990s, but is projected to decline by approximately 14% by 2030. The Amazon sink, by contrast, has already declined by approximately 1/3 since the 1990s peak, and is on track to become a net carbon source by the mid-2030s on the central trajectory. The paper's projection assumes no acceleration from El Niño shocks. A super El Niño in 2026 would arrive at a moment when the underlying baseline is already weaker than at any previous super event in the satellite era. Gatti and colleagues published in 2021 in Nature the result of aircraft profile measurements over the Amazon from 2010 through 2018. The paper showed that the southeastern Amazon, the region with the heaviest deforestation pressure, is already a net carbon source on an annual basis even before any El Niño shock in the years measured. The drying trend in the southeastern Amazon is driven both by direct deforestation and by reduced moisture recycling from upwind forest loss. Trees that should be transpiring water back into the atmosphere have been cleared, and the rainfall they would have generated downwind no longer falls. The Gatti measurements showed dry season carbon dioxide fluxes that were 5 to 10 times higher than the central Amazon background. The combination of Hubao and Gatti reframes the central question. In 1997 and 98, and in 2015 and 16, the tropical sink shut off for a year and then recovered. In 2026, the sink may shut off from a baseline that is already partially compromised, and the recovery may be slower, smaller, or, in the case of the southeastern Amazon, may not come back at all. This is the source of the point of no return concern. The Amazon has already lost approximately 17 to 20% of its original forest cover. Lovejoy and Nober, published in 2018 in Science Advances, placed the Amazon basin tipping point threshold at approximately 20 to 25% total deforestation, beyond which the basin transitions through a self-reinforcing southeast to northwest dieback front. The basin currently sits at the lower edge of that estimated range. A super El Niño on top of the existing condition is exactly the kind of perturbation that crosses a tipping threshold in a bistable system. Indonesia retains massive intact peat domes, but the combination of ongoing drainage for palm oil and pulp paper plantations and the failure to fully restore peatlands burned in 1997 and 2015 leaves the system primed. Peat that was wet in 1997 may be permanently drier in 2026 because the surface layer was burned away and the water table that the original peat depended on is now broken. The Congo Basin, the second largest contiguous tropical rainforest on Earth, has historically been less studied and less impacted than the Amazon, but the Hubao 2020 work shows the sink is already weakening there too. Dargy and colleagues published in 2017 in Nature the first systematic mapping of Congo Basin peat domes, and the carbon stocks held in those peat domes are comparable to Indonesia's. Those peat domes were not on the global radar in 1997 or 2015. They are now. The numerical projection follows. A 2026 event landing on this combined baseline could plausibly produce a Mauna Loa atmospheric carbon dioxide growth rate of 3.5 to 4.0 parts per million per year. That would be a record in the continuous instrumental measurement record. It would also be a number large enough to register publicly in a way that the previous carbon pulses did not, because the news cycle now has a quantitative threshold to track in real time. The verdict will arrive faster than after 2015 and 16. The OCO2 satellite that provided the earlier attribution data is still operating well past its design lifetime. The OCO3 instrument on the International Space Station, launched in 2019, provides additional coverage. China's TANSAT instrument adds independent measurements. The spatial attribution capability is significantly better in 2026 than it was in 2015, which means we will know whether the forests crossed the line within months of the El Niño peak, not years. There is a second cascade running in parallel to the carbon cycle question, and it has the same compound structure. A super El Niño produces drought across major agricultural regions. The standard impact list includes Indonesian palm oil, Australian wheat, Indian monsoon failure scenarios, Southern African maize, and Brazilian soybean. All of these are being forecast for the 2026 event with high confidence. The cascade is that the El Niño hits at a moment when global petrochemical supply chains have been stressed by Strait of Hormuz disruptions and Chinese sulfur export restrictions. Modern industrial agriculture depends on synthetic nitrogen fertilizer, which is produced from natural gas through the Haber-Bosch process, plus phosphate and potash inputs, plus a long list of pesticides and herbicides. All of those inputs are downstream of the petrochemical and natural gas supply chain. Drought stresses crops at the same moment input availability is constrained. Monoculture systems are particularly exposed because they rely on consistent input application to maintain yields under any kind of environmental stress. A 2026 Super El Niño, on top of constrained petrochemical inputs, would test global food system resilience in a way it has not been tested in the post-war era. The historical reference class is the 1877 and 1878 famine. That event killed an estimated 50 million people in a much smaller and less integrated global population through coupled drought, monsoon failure, and crop loss. The mortality was magnified by colonial-era food system policies that prevented relief grain from reaching famine zones. Modern grain reserves, modern transportation infrastructure, and modern aid distribution are all structurally stronger than they were in 1877. Modern dependence on industrial agricultural inputs is also greater. The two factors push in opposite directions, and the net is the open question that 2026 will start to answer. The point is not that 2026 will reproduce 1877 mortality. Modern systems have absorbed strong El Niño events repeatedly without famine-scale outcomes. The point is that the 2026 event combines a climate stressor at the upper end of the modern reference class with a petrochemical input constraint that has no clean modern precedent. The carbon cycle disruption and the food system disruption are two sides of the same large system fragility. Both reveal that the planetary infrastructures human civilization depends on were built with stability assumptions that the 2026 event tests simultaneously, and neither cascade is being priced into the public conversation. The forecast updates that matter most are arriving on a defined schedule. The spring predictability barrier breaks in May and June. NOAA's monthly ENSO discussion will sharpen the probability through summer, with each update absorbing additional ocean and atmosphere observational data. The IRI and CCSR plumes update each month. Track the September through November probability climbing, and watch whether the September, November, December probability holds above 90% through the summer. The Niño 3.4 weekly sea surface temperature reading is the early indicator. The plus 0.5 degrees Celsius threshold for an official El Niño declaration is usually crossed in mid to late summer for events of this projected magnitude. ECMWF, the UK Met Office, and the Australian Bureau of Meteorology will publish their own forecasts on parallel cadence. Convergence among the international agencies raises confidence. Divergence is informative in the opposite direction. For the carbon cycle question, the August through November Indonesian fire activity is the early indicator of whether the 1997 and 2015 peat fire pathway activates again in 2026. The Global Fire Emissions Database publishes near real-time burned area data, and the daily emissions during peak burning will be visible within days of the fire season opening. The OCO2, OCO3, and TANSAT regional flux data will provide the verdict on whether the carbon cycle response is record-breaking. That verdict should arrive within months of the El Niño peak, meaning by early 2027 we will know if the forests cross the line. For the agricultural question, the U.S. Department of Agriculture's monthly World Agricultural Supply and Demand estimates, updates through summer and autumn, are the standing reference. The Indian monsoon onset and the India Meteorological Department's seasonal update are the major decision points for South Asian agricultural exposure. The Australian Bureau of Meteorology's crop outlooks are the key indicator for Australian wheat and the rest of Southern Hemisphere agriculture. The UN, Food and Agriculture Organization's monthly food price index, is the global market side indicator. For Atlantic hurricane season, the National Hurricane Center opens routine tropical weather outlook issuance on May 15th, with the official season starting June 1st. The El Niño shear suppression timing matters for whether the 2026 hurricane season finishes above or below the elevated basin baseline. If the El Niño develops slowly and the shear suppression arrives late in the season, the August through October peak runs largely without it. If it develops fast and the shear suppression locks in early, the peak runs with significant ENSO modulation. The forecast is uncertain on that specific timing question. The timeline is clear. By October 2026, we will know if the super event scenario verified. By January 2027, we will know the carbon cycle verdict. By mid-2027, we will know if any of the speculated tipping points were crossed. And by the end of 2027, the global temperature record will reflect the full signal of the event. The most important thing to do in the next 90 days is watch the data, not the forecasts. The forecasts are doing the best they can with what is available before the spring barrier breaks. The data starts arriving in May, and it accelerates through summer. By the time the forests start responding in August, the magnitude question will be effectively resolved. And by the time the satellite carbon flux data starts publishing in autumn, the implication question will be on its way to resolution as well. This is the developing story to track. The forecast is 61% likely. The implication, if the forecast verifies, is everything.